Okay, so yesterday was a long preparation somehow towards reinforcement learning algorithms. It's been very long, but unfortunately, RL requires all these notions to be set up before entering into the actual stuff. So just to summarize the key concepts, so we have seen the concept of Markov decision process, which formalizes the interaction between the agent and the environment and the reward that is associated to the actions that we perform. And so if you remember, there was the concept of a state space, action space, transition probability that depends on, might be stochastic. And so it depends on the current state and current action, and it determines the probability of achieving a specific next state. And then there is a reward function which characterizes the quality of that specific transition as a S prime. I'm not putting you in full screen because I'm just going over these things very quickly. I will just then switch to the new slide. Second ingredient, which is very important and where we have seen, is the concept of policy. So the agents will be acting by mapping states to actions. And the way we evaluate the quality of a policy is by basically simulating, in some sense, a very long trajectory up to actually an infinite number of steps, starting from a state S. And we say that the value of a policy pi starting from state S is the sum of the rewards that I can observe, properly discounted through a coefficient gamma, and on average with respect to the random transitions that might happen during this trajectory because of the stochasticity into the environment. This was very important to set up the objective of what is the optimal policy. But as we said, it's also a very complicated object. And fortunately for us, there are Bellman equations coming to the rescue in the sense that this infinite sum of discounted rewards on average can be actually expressed in a much more compact way through this set of equations, which give rise to a linear system of equations, which means that for every specific policy pi, I'm able to compute its value by just solving a linear system of equations whenever I know R and I know P. So whenever I know these ingredients in the problem or I have a reasonable estimate of them, I can directly use this technique to compute the value function associated. Similar equations also hold for the value function associated to the optimal policy. And this is, again, at the beginning might look a little bit weird in the sense that we are saying that without even characterizing what the optimal policy is and what it looks like, we are able to say that its associated value function will need to satisfy this type of equations. The downside of this story is that unfortunately these are nonlinear equations, and so we cannot directly solve them by just solving a linear system equation as before. And that's the reason why we were later on moving to iterative or incremental algorithms to compute these optimal value functions or optimal policies. One way is value iteration, where we start from a policy and we just keep reiterating, computing basically these equations. And eventually, it turns out that this process will converge to the optimal value function. And then we are just exploiting the fact that the optimal policy is greedy. Remember that this operation, we were calling it a greedy policy with respect to this Q function. If this Q function was the optimal policy, the optimal action value function, this would be the optimal policy. But we know that this QK tends to Q star, and so taking the associated greedy policy seems like a good idea somehow. And this was further supported through the guarantees that we have, both in terms of convergence speed and the fact that if we do stop after k iterations, then we are generating, we are returning a policy which indeed performs well. Second type of strategy that we mentioned was policy iteration, which on the other hand was switching perspective and say, no, let's start directly from a policy and just try to get it better iteration after iteration. And this was achieved by this scheme where we first do a policy evaluation step and then a policy improvement. So we first estimate the quality of a policy, and then we say, now that we know how well it was performing, maybe there is an easy way to understand how to do better. And how to do better was just by computing this argmax in all possible states. And what we said is that this policy would indeed have a performance that is better or equal to the previous one. And if it's strictly equal everywhere, well, then it means that basically this policy is optimal. So this was basically what was guaranteed by this type of theorem. And then we have tried, to look a little bit at what this type of performance looks like when we try to apply it into a relatively simple maze-like problem. And this was somehow the end of yesterday's session. Now, before moving to the reinforcement learning, is there any question, any curiosity about the things that we have seen so far? Things that, either on the chat or in the room that you want me to clarify? Okay, if not, then there is somebody typing on the chat. Is there any question? Okay, so I think there is no question. Then we can jump to the properly said reinforcement learning strategies. But again, if there is any question, feel free to interrupt me at any time, of course.
Yes, Alessandro, you have a question in the chat from Jeremy, but it was just right now. I was just seeing Jeremy is writing, but.
Okay, sorry, I didn't scroll. Is it non-standard to have a probabilistic policy? Okay, this is a good question. So the question is whether the policies we are considering so far are deterministic in the sense that they really map states to actions, but does it make sense, or is it common to have stochastic policies? So I have two different answers here. So the first one is that for Markov decision processes and for optimizing the type of value functions that we have seen so far, so deterministic policies are enough. Deterministic policies are indeed optimal, and there is no gain in searching or trying to find policies that are stochastic. So in this sense, it's sufficient. Now, I have to nuance this answer in two directions. So the first one is practical. So in practice, you will see that we will inject oftentimes some randomness into the actions that we perform, not necessarily because we can do better, because again, as I said, deterministic policy is more than enough, but because we will need anyway to explore a little bit the environment, and introducing a little bit of randomness in the actions that we do can be beneficial in some sense. So this is the first answer. And so in practice, we will tend to consider also stochastic policies, at least during the learning process. And the second answer is that if I slightly change what I'm looking at, which is a Markov decision process where the function to optimize is the expected cumulative sum of returns, if I shift a little bit away from this setting, then stochastic policies out of the sudden might become the right solution. An example is, for instance, the case of games. So if I have a two-player game, so where I have two players whose actions contribute to generate the reward that I observe, then optimal policies out of the sudden might no longer be deterministic, but may be stochastic. And here we go a little bit into the field of game theory, where, for instance, the solution now becomes, for instance, computing the equilibrium of a game, and equilibrium might be requiring stochastic policies. And so, yes, in some cases, stochastic policies are even needed. Another example is where instead of maximizing the expected sum of the rewards, we might want to maximize something which is risk averse. So instead of just consider the average case, we want to be maybe a little bit more sensitive to the variance of the policy. And so if I have a policy which, on average performs well, but in some cases it might get very, very negative or bad reward, I might prefer another policy. Well, in this case, it turns out that stochastic policies might be preferable to deterministic ones. And so, unfortunately, I wouldn't say that it's very brittle as a concept, but let's say, shifting a little bit the objective function or the setting might out of the sudden make stochastic policies more desirable than deterministic ones. And again, also in practice, we will be anyway, most of the time doing a little bit of randomization. So stochastic policies, we don't talk about them, but we use them very often anyway. Okay, great. Okay, so let's jump to reinforcement learning. As I very, very briefly started mentioning yesterday, let's start with this problem. I have a fixed policy, pi, and I just want to learn how good this policy is. So I'm just considering a policy evaluation question. I'm not even asking the question of learning a good policy. The policy is provided, and I just want to assess its quality. This is important most of the time because it's one of the steps that anyway we need to solve when we want to do, for instance, policy improvement. And so we need to estimate the quality of the policy. But sometimes it's also important in itself from an application point of view because sometimes I have a policy which is running in production, let's say a recommender system, and somebody asks, okay, can we have a good understanding of how valuable this policy is, and depending on the states, or just for understanding things. And so we will be considering this type of scenario, which is now a totally online interactive scenario, where we say this outer loop here, it's basically a counter over trajectories. And then there is an inner loop here, which is over steps, what we usually call steps. So we start from, So we start from a state, and we execute actions, we observe transitions, and so on and so forth. So this thing here, we will be calling it trajectory, while each of these things, we will be calling it step. Okay, just in terms of is a full trajectory. And so we will be assuming here, just to simplify things, it's really just to make things easier in the exposition. Let's consider a problem like the one that we have seen at the end of yesterday. So a problem where I have a goal state, so this is G, and let's say that I start from this state and I need to navigate into this environment, trying to achieve the goal as fast as possible. But let's say after I hit the goal, then I might be restarting from another state. So there is a well-defined concept of termination of a trajectory, either because I reach a maximum number of steps or because I reach the goal and then I restart. From time to time, I will be calling this thing trajectory also episode, in the sense that we'll be saying, oh, an episode starts maybe from a random state or a fixed state, and an episode terminates when I reach the goal. So these are, I didn't spend a lot of time in the classification of reinforcement learning problems. This is sometimes called finite horizon or episodic reinforcement learning. But again, for me, it's really just to make things a little bit easier to explain. And then it also matches the code that we will be looking at in a short. So we start from step 0, from an initial state as 0, which, well, let's assume that it's fixed. Again, it can be random or it's fixed, doesn't really matter that much. And then we have this simulation of a trajectory where we take an action based on the policy that we need to evaluate. And the only things that we know are the outcome of this action in terms of the transition to a next state and to the reward associated to that state action operation. So you remember that even at the beginning of the algorithms like value iteration and policy iteration, I was saying that we receive as input P and R. Now, the only things that we receive in input are the policy that I want to evaluate, and if you want, in some sense, the state space. So what are the states, just to create the vector associated to the value function, and what are the actions that I can execute, or anyway, the actions that the policy will execute. So that's all I know in advance about the environment. And what I'm supposed to do is to just keep repeating this stuff for a while, and eventually try to return an estimate of the value function, which is as accurate as possible. So you see that now this is really a learning setting. I need to learn things, notably estimate a function, by samples, by direct interaction with the environment. And actually, it turns out that the problem is not that difficult at all. So I will not mention the, let's say, super basic approach, which is just to do Monte Carlo simulation. Here I will jump right into the more properly reinforcement learning approaches to this problem. And everything actually stems from the Bellman equation. So if you remember, what we know is that a function v is the value function associated to the policy pi if it satisfies this equation. Just for reference, here I'm using the shorthand notation r pi of s as r of s pi of s. And I'm using the shorthand notation p pi s prime given s as p of s prime given s pi of s. It is just for convenience. So I know that a function v is the value function v pi if it satisfies this equation. And by the way, there exists only one function that satisfies this. Again, it's a well-posed linear system of equations that admits only one solution, so there is no ambiguity somehow. There exists only one vector that satisfies this. So what we are going to do is to run this algorithm, which is called temporal difference learning, or TD0, which behaves like this. So here I'm really showing the equation, and then we will dig a little bit into what this means and why it makes sense. Although I think it will appear to be quite clear given the Bellman equation that we have seen just before. So here I'm just isolating one long trajectory of t steps. It is really just to highlight the updates that we are going to do to our estimates at each step. So we are step t. We execute the action prescribed by the policy. As I said, we observe the reward and we observe the next state. And all we are doing is to take our current estimate, v hat, and update it according to this rule. And this rule has a learning rate here. So this alpha here, alpha of st, is a learning rate, or step size, or ways of calling it. And then this is sometimes called the TD, temporal difference error. So through this terminology, you can already get a glimpse that I'm sort of doing a gradient descent, right? So I have an error which measures, so how I could reduce the error is by taking this direction, and I multiply it by a learning rate, which somehow tells me how much to correct my estimate given the current error. I will not derive this as a gradient descent algorithm, also because it's to some extent questionable whether this should be seen as a gradient descent. But we will see that somehow the gradient descent approach is what we will eventually do to generalize this type of algorithms to function approximation and more scalable algorithms. So I just want to start introducing a little bit the hinting towards that. So why is this an error? Why this makes sense? If we dig a little bit into this definition here of the temporal difference, so we say that our current estimate v hat pi on the transition that I observed at time t, so transition from st to st plus 1 and associated reward rt, is something kind of wrong by how much this is different than 0. And if we dig a little bit into this, you should start recognizing a little bit of ingredients. Now, let me just check whether, yeah, maybe I can directly show this one. So let's try to look a little bit about this formulation here. Oh, okay, now let me write it here. It's a little bit easier. So I have two components. I have this one and I have this one. So this is my current prediction. And this somehow, if I want to call this error, it means that this somehow should play the role of what I really want to estimate, right? So this should be able to measure the error. But the funny thing is that this error here is not the true value function, right? So I would be, of course, very, very accurate if I called this the error. So this, I think nobody would argue that this is not the error. It is exactly the error that I'm making. But of course, this I don't know it. So how am I supposed to measure the error if I don't know what I should be comparing to? And this is where the Bellman equation comes into the rescue. So let me just write the Bellman equations in very slightly different form. So I'm writing it, so p pi y given as t of v pi of y equals 0, right? So I'm just taking the Bellman equation, moving the right-hand side to the left, and changing sign, right? So we say that this is the Bellman equation. So once again, it means that a function v is it's the real value function if it satisfies this thing. Now let's try to derive this equation up here. Well, in a very kind of intuitive way, what I'm doing is say, okay, I don't really have v pi, and I want to measure how much v hat is not behaving like a function satisfying the Bellman equation. So I will put here my estimate. This, well, I don't really know the, let's say, the reward function associated to this, but I have observed a reward, so I will replace it by RT. And then this is the tricky part of the game. Well, I cannot really evaluate this term because this term is the expected value with respect to the transition probabilities of the value function. And this, if I don't know P, of course I don't know P pi, which means I cannot evaluate it. Well, let's be cheap. Let's just replace it with one realization of this. And I will just put v pi hat of st plus 1. Of course, what I'm implicitly leveraging here is that st plus 1 is by assumption or by construction generated from the MDP, right? So it is a sample of the distribution that is written here. But I just have that one sample. And so what I'm basically doing here is to say, okay, I could use this Bellman equation, and if I can find a function that satisfies it, I'm done. I'm not really having v pi, so I replace it by v hat, and I want to measure how much v hat does not satisfy the Bellman equation, and so how wrong my current estimate is. And I replace everything that implies knowledge of the true MDP by a sample version of it. So I'm taking a sort of simple version, simple-based version of the Bellman equation to measure how much my v hat is not satisfying the Bellman equation. And at this point, all I'm doing is to say, okay, if I'm not satisfying the Bellman equation properly, I take by how much I'm not satisfying this Bellman equation, and I will correct my estimate in that direction. Of course, I cannot do it, full throttle. Somehow I have to be a little bit more nuanced because, again, I'm taking just simple-based version of this equation. So I cannot trust my estimate of the error 100%, and that's the reason why we will eventually take a learning rate which measures somehow how much I want to correct by the estimated Bellman error that I have according to this current transition and the current estimate that I have. So this is somehow the thought process to get to understanding why this makes sense. So in terms of the content of the slide, basically we can say that the error of the function v in terms of Bellman error, so how much it does not respect the Bellman equation, it can be measured this way. So this is by how much the function is not the true value function. So much so that if I had the true value function, this would be equal to 0 by Bellman equations. Now what I have is that if I take this expression out here and I condition on ST, so I'm really fixing this one and just considering the fact that I observed possibly a random transition and random realizations are T and ST plus 1, and I take the expectation with respect to the two, well, then what I'm getting is RTST, right? It's, let's say, the expected value of this RT plus gamma. And then I take the expectation of this, and the expectation of this, I can write it this way. It's the probability, it's the expectation of with respect to obtaining ST plus 1. And then I put here the V hat, which is this part here. But now if I look at this expression, this is exactly what I wrote here, just applied to V hat pi and ST. So I can confidently say that this temporal difference error is just a noisy observation of the true Bellman error. And so if I knew the true Bellman error, then it would be trivial to solve the problem because I could just find which function satisfy, which drives this to 0. But okay, since I cannot evaluate the Bellman error exactly, I have an estimate. This estimate is unbiased, which means that overall I'm kind of doing something reasonable. And so on average, I can say that what TD, temporal difference algorithm, is doing, on average, remember that the algorithm is updating this by taking the previous estimate and correcting it by alpha ST delta T. Instead of doing this equation, on average, what I would be doing is this one. So the reason why I mentioned this expected dynamics is because if maybe for some of you rings a bell, one way to prove that temporal difference is a good algorithm is actually to study its expected dynamics, move it to a continuous time, analyze the associated ODE, and showing the convergence properties of this ODE. And this will be one path to prove good properties about this algorithm. There are other ways which interpret this more as a sort of SGD, stochastic gradient descent type of algorithm, and so the proof takes a slightly different perspective. So I just want to mention, to give pointers to what are the technical ingredients that we usually use to have an even deeper understanding of what this algorithm is doing. But let's say that I hope that by drawing the connection to the Bellman equations and measuring the errors in that sense, it gives enough somehow intuition about where this algorithm is coming from. There is also a slightly different perspective that we can think of. So again, if you take this equation here and you explode the temporal difference part, you can also rewrite it this way. And this is yet another perspective, which is more the one of stochastic approximation, where basically we are taking a weighted average between the previous estimate, the old estimate, and then I can think about this one as the new estimate or the one step forward estimate of the current value function, because again, we know that the true value function would be equal to this r plus gamma expected value of v pi in the next state. And so somehow I'm saying, okay, this is, a new estimate, which is leveraging, this new information rt and st plus 1 that I have. And so I take a weighted combination of the two, and this is going to be my new update. So it's yet another, view of the same thing. I think this one is more, intuitive. It speaks a little bit more, but this one is another point of view. I just want to stress that it's when you look at this type of stuff for the first time, it's really surprising that it works, that it goes anywhere. Because so let's look at what we are doing here. We start with the value function, which is arbitrary. I mean, this I should have called it v hat. So v hat, which is totally arbitrary. And then the way I update my estimates is by using my estimates, right? So it's really weird that I'm saying, oh, I correct this v hat by how wrong my v hat is as evaluated according to my v hat itself. So this seems like a chicken and egg problem, right? The only thing that I know is v hat, and I'm correcting v hat with v hat, but v hat is wrong. So what am I doing here? So this is sometimes in reinforcement learning is called bootstrapping your estimates, because indeed you use your estimate to generate an estimate. So that's the reason why it's sometimes called like bootstrapping in statistics. But again, the reason why this works is that this is really like an estimate of the Bellman error. And if you think about it this way, then everything becomes a little bit more sensible. So I'm not using my estimate to compute errors. I really this one is directly estimating how much v hat is wrong in a Bellman equation sense. But that's the reason why somehow it's not that crazy, this stuff. And the reason why it's not that crazy, it's also somehow supported by an important theory behind it, which says the following. So let's read a little bit through this statement. It says that if I run the temporal difference algorithm with learning rates that decay in a proper way, depending on each state, how many times I observe that state. I will clarify this in a second. And if the way the learning rate decreases satisfies specific conditions, then what we have is that almost surely, so it's a strong statement, almost surely v hat will converge to v pi in every state. So let's dig a little bit more into what are the conditions that need to be satisfied here. So what I'm saying is that alpha, the learning rate, is dependent on the state. It's an alpha of s. And the way I make it dependent, so it's alpha t of s, is that I will make it decrease the more I did observe the state. So this nt of s, I will be using it to denote the number of times I visited that state. And so I will be just saying that my learning rate will be smaller for states that have been visited many times, and it will be larger for states that I have not visited much. And the way it decreases is crucial for the convergence and for the convergence speed. So for the convergence itself, the conditions are actually quite mild. So what we are asking from the learning rate is that it, with the number of samples, is it's not decreasing too fast. so that the series of alpha t is actually divergent, which means that alpha t does not decrease too fast, but it's decreasing not too slowly because the squared series is actually convergent. So these, you might have seen these conditions before in other fields. Sometimes are called Robbins-Morris conditions. And again, they give quite a broad set of learning rates that still would justify the final almost sure convergence, which is reported here. What are common choices? So here you see an instance. So basically, we just take the current number of times I visit that state, and I put 1 over nt to the beta, where beta is a coefficient, let's say, between half and 1. And any choice in there would satisfy these inequalities, and so I would be fine somehow. So if I think about it, basically all we're saying is that with time or with number of visits, the learning rate should not converge too fast to 0, it should not converge too slowly to 0, and pretty much anything in terms of schedule that I put in between will still guarantee the convergence. So this grade is a very strong result. It's very nice. Of course, it has, it's somehow a proof that our method is sound. It doesn't really say that our method is good. Just say that it's sound. It does converge almost surely asymptotically. If we want to have more characterizations like the variance of this estimator, how fast this converges to 0, and so on and so forth, we need a little bit more sophisticated arguments, and definitely we need also to be more careful about the learning rate that we use. And now choosing an appropriate learning rate will have an impact on the overall variance and convergence speed of this. But for us, let's say that it's just a sort of support for soundness of our method. And then also, let me say that in practice nowadays, how people would usually work with this type of problems in practice is to set the different learning rates, do cross-validation, hyperparameter optimization, and then pick the one which works best. So overall, it's good to have a guidance. It's good to have a proof that things are sound. But on the specific learning rate that we are going to take, it's mostly an empirical question, which oftentimes is mostly problem-driven. And so it will be chosen by experiments. Just to illustrate a little bit of this, or actually maybe in the interest of time, I would actually skip this example, which is not that informative anyway. Yeah, let me. So I will not describe the problem. I will not discuss much about this. Let me, and not by this either. So let me just illustrate the blue curves. The blue curve on the y-axis is just the mean square error. So basically, we are taking the average over states of the error that our prediction makes on that state after n episodes. So let's say this n minus the true one. So let's say that this problem, we know the true one. So it's really just for illustrative purposes. And so here you see different curves depending on the learning rate. And here are fixed learning rates. And fixed learning rates, they do not satisfy these, right? Because of course it would sum up to infinity, but the squared would also sum up to infinity. So they're not guaranteed to lead to a convergent process. But just for illustration, so if you put a very slow learning rate like 0.05, you see that the error decreases slowly, but it goes down to a lower level than the one that you would have with a stronger learning rate like 0.1 or 0.15, which they tend to converge faster, but then they would not converge to 0 because anyway I have this constant learning rate which keeps perturbing my estimates. So eventually you see that in some sense, the ideal thing is to start with a large alpha, which means anyway, my current initial estimates will be wrong. So let's rather update very quickly and then little by little to decrease the alpha so that we indeed go to zero as prescribed by the theory. But again, I can tell you that in practice, most of the people would just be happy with a good enough estimate of the value function and would rather maybe favor larger learning rates to be able to just getting good estimates fast, and then that's fine, right? I mean, we don't care to be perfect anyway. Okay, are there any questions about this? This hopefully, if you have a clear understanding of the Bellman equations, moving to this type of completely interactive algorithm, it should be relatively smooth, the step that we are doing here. And any question, either in the room or on the chat?
Yes.
Okay.
There is a question.
Yeah.
Sorry.
Okay, great.
Maybe you mentioned, but I didn't hear. Is there a good strategy for choosing alpha or updating alpha through the iterations?
Yeah, so I would say, as far as we are concerned in the, let's say, in the exact tabular case, finite number of states, and so on and so forth, most of the time it will be something like this, in the sense that we will be storing the number of times we visited that state. And when we have to apply our update on that state, we will just say that the learning rate is 1 over the number of states to the power of, most of the time it will be half, to be honest, so it will be something like 1 over square root of n, maybe something a little bit more, but that's, let's say, sort of first choice. It's oftentimes something like this. As I was mentioning previously, in practice, when we will move to more complex algorithms, we will have just one learning rate and not a state-dependent learning rate. And how to tune that, again, it will be mostly a matter of empirical validation by hyperparameter optimization or something like this.
Okay, thanks.
Yeah, sure.
Other question? No? Okay.
Okay, so now we have this first ingredient, which is the steady learning algorithm. And the disappointing part is that it's still just about evaluating the value of a policy. So it's not really trying to learn the optimal policy. But we will see now in step 2 and step 3 that moving from this algorithm to algorithms that actually learn the optimal policy is not such a big step. So now we put as an objective, the objective not of policy estimation, but let's say optimal policy learning. So we really want to learn an optimal policy, and we start with nothing. I mean, we just start with no prior knowledge about the environment, no policy. And so we have to just make up our mind about what is good and what is bad in doing by interaction with the system. So now the game will be again over multiple episodes of trajectories, start from a state, interact with the system by taking actions. And you see that previously this action was prescribed by the policy, right? So it was something like this. Now I don't have a policy to evaluate, so this is, well, take an action, and we will see what are the possible choices here. Observe this and keep going. And after a while, I will be asking, what is your current estimate of the optimal policy? So the first type of strategy that we are going to see is sometimes called actor-critic methods, which very much leverage the previous ingredient of temporal difference learning, and in some sense is also based on the policy iteration algorithm. So you remember that we had, if we knew P and R, we had two strategies to compute the optimal policy: value iteration or policy iteration. Now we will be taking a little bit this perspective to derive what is called an actor critic algorithm, that is, again, a pure RL algorithm interacting with this. So as much as for computing this, we will be computing this as a fixed point of the Bellman equation, and -1, and then we were using this to derive the TD. Now we do the same. We go back to what we know about computing optimal policies, and we will try to make a sample-based version of it. And again, it will be the actor critic. So the actor critic has also a little bit of more, how can I say? So, by the way, okay, if anybody cares about this type of connection, I would like also to mention the temporal difference learning and actor critic methods. When they were first proposed as methods for learning either value functions or policies, actually they had a very, very strong psychology or neuroscience backup, in the sense that probably if you attend a more computational psychology or neuroscience course where they mention anything about reinforcement learning, they would link temporal difference learning to the way synapses works and how synapses are reinforced by something which is a gap between what we expect, which is V of pi, and what we observe, which is that R plus gamma V of pi. So oftentimes, even from also chemical point of view, there are some conjectures that type of update is a good model for also how synapses get reinforced. And similarly, also these actor critic structures have been originally actually proposed with a lot of inspiration from psychology. And the reasoning is the following. Basically, there is a component in our agent, let's say, which is called the actor, which just tries to do actions. So it's responsible for performing actions based on the current state. So if you want, this is the policy in some sense. And then there is a critic which evaluates how well the actor is behaving. Plus, it's also suggesting to the actor where there are opportunities of doing better. So this is doing a critical analysis of how well the actor is behaving and whether there are opportunities of improving what it's doing. And we'll be, focusing on these two ingredients and see how they can be formalized. But overall, the idea is that now if I have something that execute policies over time, and then I have another component which on the side is evaluating how well this performs and is also finding possibly way for the actor to improve performance, then effectively what I have is an algorithm that learns better and better policies. And if you remember the scheme of policy iteration, well, we had these two ingredients. We had the policy evaluation step, which is basically what the critic is about. And then we had the policy improvement step, which is what the actor is supposed to do given the evidence provided by the critic. So we were trying, given the evaluation of how well we are performing, maybe there is a way to do better. And this was the job of the policy improvement step or of the actor in this terminology. Okay, so let's, so this was, again, the scheme that we had in value iteration, in policy iteration. Notice that here I have a slightly different version than the one that we initially looked at. I'm not going to go through this, but it's the same algorithm. It's just rephrased through action value functions instead of value functions. But let's just jump directly into this this type of algorithm. Okay, so the critic part, which is doing policy evaluation, by now we know how to do it from samples. TD learning, right? TD learning, it says, give me a policy as input, and I will try to estimate how well it performs. So I'm, pretty much well equipped on the policy evaluation step. There are also extensions of this algorithm that, given a policy, they also try to estimate the action value function associated to this policy. But the scheme is more or less the same. So that's the reason why I was, mostly looking into first the value-based and non-action value-based, just because the equations are simpler to treat. But somehow to say that, the same scheme can be applied to learn action value functions. Okay, then I have to do the policy improvement. And the policy improvement, if you remember from policy iteration, it was working like this. In all states, we were supposed to take an action which would maximize the immediate reward plus gamma, the expected value of v by k in y. This is what we've seen yesterday, right? Now, the problem is that anyway, I cannot really do this. And this is the reason why usually we move to action value functions, because in action value functions, I don't know how to make this disappear. Sorry about that. Because in action value functions, this thing can be conveniently rewritten like this. Q pi k SA. Okay, so this is much more convenient. Now, if I get an estimate of this Q hat, I would be able to compute directly the greedy policy, even without any knowledge of the MDP, right? So that's the reason why we prefer action value functions, because even without knowing the MDP, it's the policy improvement is a step that I can do. Actually, in practice, we use different formulations of how the actor works based on what the critic has learned. And strategies are of this kind. So the first one is what I just wrote in the previous slide. So we say that the policy that we deduce is by taking what the critic has learned so far, and I will just take the action which maximizes the associated action value function. Usually this is not really desirable as a strategy, although it's well justified, it's well motivated, because that's what we would be doing in policy iteration. It actually turns out that it has issues of not exploring enough. And so usually we use either of these two strategies. So one is called epsilon greedy, and the other one is just a simple softmax. So the epsilon greedy basically says that I will define a policy pi q so that in the state S, I pick an action A at random. So just linking back to the question that I had at the beginning of the class today, we move to the case now where we use stochastic policies. So we say that the actor will be a stochastic policy grounded in Q, in the current critic estimate, where with probability epsilon, I will just take an action at random in the action set. And with probability 1 minus epsilon, I will be taking the greedy action, so the one which indeed maximizes the current critic evaluation. Alternatively, so this is a very sharp randomization. Either I take something totally at random or I'm explicitly greedy. A smoother way of doing this is by doing just a softmax operation with some temperature level tau. So you probably have seen this also in other contexts. Softmax over a vector is just the normalized exponential of the vector. So this clearly is a distribution, is a well-defined probability distribution, because if I sum over actions, it sums up to 1. And tau is a temperature, because if I let tau tend to infinity, then this will be just a uniform. And as tau tends to 0, this will tend to converge towards the greedy, so giving a much larger probability to the action with large Q values. So these are just some examples about how we can define an actor based on what the critic has learned so far about what the actor has been doing. So once again, you see a little bit this chicken and egg problem, right? In the sense that the critic is supposed to evaluate what the actor is doing, and the actor wants to improve over what the critic tells you. So
Alessandro?
Of course, there is a little bit of, yeah.
Sorry, you had a question on the chat asking if epsilon is kept constant over the iterations or not.
In practice, no. It will be annealed towards zero, a little bit like the learning rate that we mentioned before. So either the epsilon will go to zero, or in this case, the tau will go to zero, and so we will tend to converge towards the greedy policy. So as I was saying, so there is still a little bit of this chicken and egg problem, so the critic, as I said, it can, so there is a little bit of this chicken and egg problem where the critic is supposed to evaluate the current policy, but the current policy depends also on what the critic works. So it's again a non-trivial problem to analyze and then to understand. But once again, the algorithm is sound, and if things are done properly, then it's still guaranteed to get better and better policies over time. In the limit, basically what you can think about is just saying, I run the critic for a long time with the fixed actor, and then what I'm doing is basically pure policy evaluation. Then after this long phase of policy evaluation, I will change the actor either this way or this way. I freeze it. I let the critic learn a new Q value. Then I will freeze the critic. I will compute the new actor, freeze the actor, learn the new critic, and so on and so forth. So in the limit, you can think about this as just mimicking policy iteration. But the way we do it is where these two phases of policy evaluation and policy improvement are much more interleaved one with each other. Plus, as I was saying, a little bit of randomization applied here. So in this slide, there are the specific equations that you need to use for the update of the critic with action value functions. It's the same equations as before. It's really just using the Bellman equations for action value function instead of value function, but you see that it's the same scheme. When we do this for V functions, the algorithm is called TD learning. When we do it for Q function, this algorithm is called SARSA, historically. But otherwise, again, they're the same scheme overall. So now let's look a little bit, when we put all these ingredients together, what the algorithm looks like. The algorithm looks like this. It says, initialize your action value function to something, and then over steps, over trajectories, and so on and so forth, what you can do is to execute the action prescribed by this actor, and the actor can be formalized, this parenthesis missing, through softmax or this epsilon greedy policy that prescribes which action to take. I observe the outcome of that action. I will decide which action to take next, and then I will be just doing TD learning on this. And this is the update of the critic. So this is the actor, and this is the critic. So if you notice, I'm not explicitly calling this an update of the actor because the actor is directly computed on the basis of the Q values. We will see, hopefully, towards the end of today, that the practical algorithms based on this actor-critic idea, they also do a smoother update of the actor. So they will not be really computing the actor this way, but they will, having a properly set update rule for it, which of course is still guided by the critic, but it's not as explicit as this one. So again, the nice properties of these, here I don't report it really as a theorem because things are a little bit more complicated, but intuitively we know from TD learning that updating the critic this way is the right way to converge to the value of that policy. I know that this form of the critic is improving because it's almost like taking the greedy policy. So it's improving with respect to the current policy estimated by the critic. So each of the two ingredients, this one is doing the policy evaluation in an approximate incremental way. This is doing the policy improvement in an approximate incremental way. And so it's reasonable to say that as tau tends to 0, as epsilon tends to 0, and so this becomes really the greedy policy, I will naturally tend to converge to the optimal policy, and Q will tend to converge to Q star, because pi tends to, somehow the chain is that pi will tend to be better and better, and so Q hat, which tends to converge to Q pi, but Q pi itself tends to Q star, and so this, eventually is the chain. But again, everything is, interleaved and entangled together. So analyzing this type of algorithms is definitely non-trivial. But, I just want to, again, convey the message that they're sound and they follow sound intuitions in the way they're defined. What are the limitations of this type of algorithms? Well, the limitation is what sometimes in reinforcement learning we call on-policy learning. So if you see how this is defined, is updating this Q value in order to try to do the critic job, which is to estimate how well my current policy is behaving, right? So I want to estimate the current policy. And in order to estimate the current policy, I have to execute the current policy, right? The actions have to be prescribed by the policy that I want to evaluate. That was also the case for TD learning. Of course, there are variants of these where this can be relaxed a little bit, but otherwise these are so-called on-policy learning algorithms because they really need to execute the policy that I care about in order to be sound and converge to reasonable things. Then, of course, I can keep changing my policy, but every time I change to a policy, I will be executing that one to collect samples and to update my estimates through the critic. Now, this sometimes is not that desirable in the sense that if I could, I would like to have an extra degree of freedom of saying, you know what, you're free to explore the environment however you like. So you don't need to be somehow tied to a specific Q value or to a specific policy. Just try to explore the environment, understand how it behaves, how it looks like, where the rewards are, and so on and so forth. And while you're doing this, try to evaluate what a good policy would look like. So here now I'm disentangling completely the policy that I execute to collect information and the policy that, if asked, I will be returning as the good one. So here the two things are deeply entangled. The policy that I execute and the policy that I return are the same thing. While a kind of desirable property would be an algorithm that decouples the two so that I have much more degrees of freedom in exploring the environment freely without being tied to a specific policy. And this is what we do when we move to off-policy learning, and notably what we do with Q-learning, which will be the first algorithm that we go and implement in a few minutes. I will pause at the end of Q-learning to ask questions and revise this concept that we have so far. So we'll now just jump to this because it's actually just a couple of slides. And the reason why it's just a couple of slides is that, remember I said that we have Bellman equations for a fixed policy. We use them to derive TD learning. And then we had to compute the optimal policy, we have either value iteration and policy iteration. Policy iteration ideas, we use them to derive actor critic. Well, let's be greedy and let's try to exploit value iteration concepts to derive Q-learning, which is another algorithm to compute optimal policies, to learn optimal policies. And the starting point is very similar to the one of TD. So remember that there was such a thing as optimal Bellman equations. Here I express them for action value functions, so for Q star. We know that the action value function associated to the optimal policy must satisfy these equations. And as a byproduct, we also had that the optimal policy would be the one which is greedy with respect to Q star. So once again, a little bit like in value iteration, if I have now a learning algorithm that is able to estimate Q star well, then I will be able to derive the optimal policy by just taking the greedy value. Remember that in value iteration, it's exactly what we were doing. We were saying, I stopped after a while, I have a specific action value function, and I will be returning the associated greedy policy. And hopefully, if my algorithm is sound, this will tend to this, and so this will be a better and better policy and will be approximate what pi star would do. Okay, so this is the first intuition. The second intuition is that, well, for TD, we were doing this. We were saying, oh, let's take the Bellman equation, let's rewrite it this way. And let's just use as a proxy for how wrong our estimates are. And let's replace whatever I don't know with just its simple base version. So this we had of ST plus 1. Well, then maybe we can apply the very same game, this very same concept to this equation here. So we know that a function Q is a good proxy for Q star if it satisfies this equation as accurately as possible. So if I have an estimate Q hat, I will try just to correct it in order to try to make this equation as true as possible. Once again, I don't really know this P. I might not even know exactly this R completely, and I will be just replacing them by samples. And what we obtain is now this algorithm. It's called Q-learning because it's learning Q functions or Q star functions more directly. So it takes an action AT, it observes the associated reward and an associated next state. And the way we update Q hat, and now Q hat has the ambition of approximating Q star. While previously it was, Q hat was just trying to approximate Q pi. So this was in actor critic. Now we're really trying to approximate Q star. And so we will be using this as our temporal difference learning. So by how much? A sample-based version of our Bellman equation is not satisfied. Learning rate alpha as much as before, and the shape of the update is the same. Now, there is also another ingredient which is very different from what we assumed so previously, which is the fact that here I'm saying, well, take an action according to a policy pi t. If you notice, there's no pi t that appears anywhere here. So pi t is just a free variable in some sense that I can choose, and I will try to choose it in order to make the algorithm exploring efficiently and so on and so forth. And so we will see that eventually we'll fall back into standard type of policies. But just to say that this, for the construction of the algorithm, is totally a free variable. I just take an action according to some criterion. And then this, I can still apply it independently from how AT has been chosen. Because, for instance, when I have to evaluate the quality of the next state, I'm always taking the greedy action here, independently from what AT plus 1 will be. So in this sense, now I'm off policy because I really don't care about what your current policy prescribes. I will just be trying to approximate Q star altogether. So much so that the output of the algorithm is not even connected to this pi t, and it will be just the greedy policy as computed with respect to Q hat. So again, just to recall, a greedy policy will be basically just this one, the one that maximizes the Q that I return at the end of my process. And again, the similar things that we said before, which are if I set the learning rate properly and so on and so forth, then this will naturally tend to converge to Q star. So the intuitions that we have behind TD learning, they also apply to Q learning as well. So much that we have this type of guarantee if the learning rate satisfies something similar as the Robbins-Monroe conditions that I had before, then almost surely Q hat will converge to Q star. Now, there is only one caveat here, which is very important, which is this one, that the first time you read it doesn't mean anything, honestly. It says all state action pairs, so all state actions, are tried or visited infinitely often. So let me just parse this infinitely often a second. So imagine that I observe S1, A1 for an infinite number of times, and then I shift to S1, A2, I observe it an infinite number of times, and then I move to S1, A3, and so on and so forth. So this is not infinitely often. So I observe this infinitely, but not often. Infinitely often means that the sequence with which I observe state and actions is interleaved one each other. So basically, there's no starvation, because if I infinitely observe this one and then I never observe it, then it means that I will not update this anymore, and then the algorithm is not convergent. So otherwise stated, beyond this one, it's just what I'm asking is that you keep exploring the environment so that you keep observing state and actions many, many times, and it's not that you stop exploring a part of the environment after a finite number of steps and say, oh, fine, I stop going there because I know everything. Because otherwise, of course, you will stop updating your Q values in that area, in that region, which means that eventually you will not be converging exactly to Q star. So that's what this funny expression means. So as I said, this is an off-policy algorithm in the sense I don't really care which policy is executed to be doing my update. And before going to the handout session and maybe passing through the questions, let me just show one example. So through maybe simple or maybe a simpler one, and let me reduce the stochasticity of the problem. So this is a little bit what I tried to sketch very quickly at the end of yesterday, but let me just spend maybe one more minute on this. So this is the type of environment where the agent needs to navigate from, in this case, the initial state is fixed, to this state, which is the goal. And whenever you bumped into the walls, it's a penalty of 50. Otherwise, every move is a penalty of 1, except when you reach the goal where you don't have any penalty. So now the thing that I will be illustrating is the dynamics of the Q-learning algorithm. So we initialize the algorithm. And so these numbers here are, let me try to see what I can do. Something like this. Yeah. Let's see. Right. So we said that Q-learning works on Q values. And so what the numbers that I'm seeing here is just the Q values. This is the Q value of this state for the action going up. This is the Q value of this state for the action going right, and so on and so forth. The little smiley is where the agent is. And the way the pi t that I mentioned before is defined in this specific implementation of Q-learning is this epsilon greedy strategy. So it will say if I'm in a state S, I will be executing the argmax of my current estimate Q hat time t in the current state with probability 1 minus epsilon, and I will take an action at random with probability epsilon. So this is the so-called epsilon greedy exploration strategy. There are plenty of other strategies that we could use. This is a convenient one. Fair enough. Let's keep this one. And so you will be seeing that sometimes it doesn't really do what the argmax prescribes, and sometimes it just does some random stuff, and this is just by randomness.
Alessandro?
Yes?
Yes, just you have some question in the chat about what you have said for the penalty, for the wall and so on.
Yes. So if we take one step and we don't bump into a wall, there is still a penalty of 1. And this is done so as to kind of incentivate the agent to reach the goal as fast as possible. Because whenever I take an action, I get a reward of -1. And so if I can reach the goal very fast, this will be my way of maximizing the reward, or otherwise minimize the cost. So it's just a way of pushing the agent to go towards the goal fast. Okay, so now let's see what happens. Let's take one step. So one step, what we do is to, in this case, is take the action up. So we would like to update the state, let's say this one, for the action going up, and the equation of Q-learning, it tells us to do the following. So alpha times the reward that you observe plus gamma, the maximum of Q of the state that you observe, let me call it as prime, maximum of A prime, minus your current estimate. Okay, so let's look at what probably looks like in this case. So this is initialized at 0. The alpha, it's up here, is initialized to 0.7. R, well, it's -1. It's the cost that we have. The Q values in the state that we reach, which it turns out that in this case is this state here, it's 0 everywhere. So also its maximum is 0 times gamma, it's 0. It's +0 minus the Q value that I had at the beginning, which was, well, 0. Okay, so what I should expect is a -0.7. So as I mentioned yesterday, in this thing here, first I think they display things at finite precision, and additionally they show the cost version. So that's the reason why Here, if you can read, we observe a 0.7 and not a minus 0.7. Okay, so basically that's what my algorithm is doing. It's executing Q-learning, and it observed this. And now, I like somehow to make this a little bit more, let's say, try to be a little bit empathic to the job that this agent has to do. So what we are asking to this agent is, we are telling this agent that there are 9 states labeled from 1 to 9. I have no knowledge about how they are arranged, what is their meaning. I tell the agent that you have 4 actions to take in each state, which are 1, 2, 3, and 4. So no meaning, no semantics attached to it. And what you have observed is that you were in state 1, you took action 1, you observed a reward of 0, and you ended up in state 2. And that's all you know, right? I mean, this is what a single sample in reinforcement learning is telling you, which I think we can confidently say that it's pretty much nothing, right? One sample contains so little information that it's expected that these algorithms, they take a while to converge to anything sensible. So if you had to solve this problem, on a piece of paper, and I told you just this number, you were in state 1, you ended up in state 2 by taking action 1, and this was associated with a reward of -1, you would not be able to, get much of a sense of what's going on. Of course, usually we are biased because we see that it's a maze, we know that there are walls, we know that there is a goal, we know that the objective is to get to the goal as fast as possible. So typically when we observe this agent moving around, we say, oh, but this is such a stupid algorithm, right? It doesn't work. But usually because we just impose our prior knowledge and our bias in observing these, which conveys a lot of knowledge about the problem that the agent doesn't really have. So let's try just to simulate one full episode, so you will see that it's moving very fast. And so an episode terminates when, by luck, this stage, it reaches the goal. And imagine that I just have this single trajectory and I have to return a policy. As we said, the policy that Q-learning returns is just the greedy policy with respect to the function that I learned so far. And this is these white lines here. And you see that, well, unfortunately, if I stop here, well, I didn't really learn much. Here I learned not to go up, then I learned to go down, and that's pretty much the end of the story, right? So if the environment was deterministic, basically I would just stay here trapped into this up and down forever. And that's the reason why we need to inject some randomness. So if we were stuck to what we believe is a good policy, maybe this good policy is not good at all, and we would not be learning anything more, right, from just keep repeating these things. While if we, from time to time explore and try other things, we might be maybe doing something which is really bad, but possibly maybe learn something which is better and learn how to improve our estimates and our policy. Notice that, again, maybe what it's currently learned is not even that much off, in the sense that if you imagine to look back at what was the experience of this little agent, and imagine that by very much bad luck, imagine that when I tried the action down here, by randomness, I bumped into a wall. And then I got a -50, right? A huge negative reward. So I might be very well convinced that that's really a bad action. Of course, I mitigate it by the learning rate, right? So I'm not taking it as the full truth because I'm not entirely sure that that's the true value, because there is stochasticity, there are current estimates that I have. So I mitigate it by the learning rate. But you see that, for instance, let's see if there is any of these unlucky things. Well, not that much, because I made it quite deterministic now. But if the environment is quite stochastic, it might very well be that the action which, if I knew it's the optimal one, at the beginning might be rewarded very badly just because of bad luck. And this will take a lot of evidence and a lot of exploration before counteracting these initial negative samples from the environment. And this is a little bit what, in the rush, I kind of ended up doing yesterday, where, it took really a while to learn anything reasonable. So now hopefully I made it a little bit more deterministic, and the environment is also much smaller. So hopefully in just a bunch of episodes, we learn something decent. So now we learn through 3 episodes, I think 3 or 4 times. It looks like we are doing good, right? Up, right, down. Oh, here we still really didn't get what's the right action, right? So once again, if I was to freeze the current policy, what I would obtain is really something bad, right? Because it would be a policy that would never, or very, very low probability, reach the goal, and it would just be stuck in going up and down here. So let's go again, a couple more of episodes. And you see that sometimes episodes are very long, right? Because it might not even reach the goal. Okay, so let's look at what we learn now. And it's kind of curious because now we look something decent. It's up, right, down. And then we ended up in what we would normally call a local optima, right? So we go left, we go down, and we go right. We do achieve the goal, but not in the fastest way. The fastest way would be to take action down. But look at what is the current value that we attribute to action down. It's 35. So it's minus 35, right? Which means that, unfortunately, it might have happened a few times that I tried this action down, but again, by randomness, I ended up bumping against the wall. And so now I'm convinced that that action is really bad. And so it's much better to take this path. And this path, on the other hand, it consistently led to the goal. And so I'm much more confident. So let's just try to simulate a little bit what is the dynamics of the algorithm. And then I wrap up and we go to the break. What might happen now, it's 2 things. So the first one is that I do this path a few times. I end up here. And then maybe by just pure luck, by exploration, I try a few more times action down. And I realize that it's actually better than going left. This is one option. There is another option, which is less nice, which is I confidently go down here, and then it happens that I go right, and in that specific realization, I bump against the wall, and I do not reach the goal. Then I might start questioning whether this is that good action. Maybe the good action is going up again. Right? Because if this one has a reward which is, I don't know, or an estimate of the Q value which is minus, 40. This one is 35. This is 53. Well, maybe you know what? It's better to go up. And so it might even happen, and believe me, this happened, that I see progress and I say, oh, you see, it's learning something good. And then the performance degrades again because of, again, the randomness and so on and so forth. Of course, this cannot happen forever because the learning rate decreases, the exploration learn decreases, and so eventually we tend to a stable and good policy. But just to say that, the performance is not perfectly going up always and forever. It has a little bit of jiggering around a nice learning curve. So just out of curiosity, let's see what happens here. So really kind of stuck to this strategy, and maybe the exploration now it's too low to hope for observing a much better policy. So probably this is an example where the exploration is too low to allow the agent to explore anything outside. So it's a little bit like when we do optimization, we got stuck into a local optimum, and you have to really to jump it back through a little bit of exploration. Oh, okay, so now something happened. We see that it got the wrong action here, but this incentivized to stay more here, which allowed it to learn more about going down. And now it's consolidating a little bit more the more straightforward policy, which is here to go down directly, which is clearly preferable with respect to taking this one. And now, even if it will happen that maybe I'm taking unfortunate realization, hopefully learning rates now are much smaller because they've been decayed. And so I will not shift this one too much so as to change my mind about what is the optimal action here. Anyway, this is just to illustrate a little bit what are the difficulties that these algorithms are facing and why doing reinforcement learning is not trivial. And I remember my good old times during the master thesis that it was incredibly frustrating to see what these algorithms are doing. So usually my suggestion is don't look at it. So just let it run for a while and then wait for what is the answer. Because when you look at it, you tend to interpret too much about what the algorithm has been doing and what it's learning. While again, it's very much black box for the agent, what the environment looks like. And so it's a little bit unfair to charge it with expectations based on the knowledge of the problem that we have. I went a little bit out of time. We'll still try to keep the restarting maybe back at 4. If it's okay, maybe we can just take another few minutes of break. So I will start at 5, at 4:05. And we will start coding this algorithm and try to see how it behaves in a slightly different problem. Again, if there are questions, I'm around, so feel free to stick around and ask questions. For the others, feel free to go to the break.
Yes, thank you very much. Questions? Yes.
Excuse me. You said that for this experience, the action going down was seen as a bad action for the agent. So do you mean this in the sense of in all the paths he tried, a lot of times this action led to a wall? Or
Actually, if you look at the numbers, it's enough just one unfortunate execution to start believing that. In the sense that, so imagine that I have an estimate for, let's say, this state, action going down, which is something like this, let's say 1.0, right? And this other one, so Q in the same state for going left is 6. So you would say going down is clearly better than going left. Again, remember that these are coasts, right? But now imagine that I'm executing this action as prescribed by this guy, and I'm not very lucky. And when I'm in this state, I perform this, and I stay in this state, and I observe a penalty of 50 because I bumped into the wall, right? So I bumped here, and I stay in this state. Then let's look at what would be the new value. So the new value of this one, let's apply Q learning update, is 1 plus the learning rate that we have at this stage. And then 50 plus gamma, let's set it equal to 1. Here, instead of the maximum, I should take the minimum over the Q value of the state as prime that I reach over actions minus the previous estimate, which was 1. Now, S prime, we said it is equal to S. And so we know that the minimum over Q values in this state is 1. And so what the update will look like is 1 plus alpha, 50 plus 1 minus 1. So it's 1 plus alpha 50. So you see that as soon as I have a slightly large alpha, then it's very easy to make this bigger than 6, even because of just one single unfortunate realization. Of course, over time, this will not happen anymore because alpha decreases down to 0. So single unlucky transitions will not play such a bad effect on my beliefs anymore. But in particular, at the early phases of the learning, what I say is that, well, my estimates are wrong anyway. There is a bad transition. Well, I should be very careful because maybe this is not the right action. You can also think about it the other way around. Imagine that you were just been lucky and you tried the action right a couple of times and it went down. And so you attributed just the cost of 1, while the true cost is 50 somehow, or almost 50. So you want to be reactive to samples, but not too much, because you also don't want to destroy the knowledge that you accumulated so far. So the more knowledge you've been using, the more conservative you want to be skewing it, and the smaller your alpha learning rate will be. But when rewards are very large, it means that basically it's like a variance, a random variable. I have a huge variance, and so I have to average a lot of things before converging to something more stable.
Okay, thank you very much.
Does that address the question?
Yes, thank you very much.
So there is also a question on the chat. What is the gamma in this simulation? The gamma is equal to 1. In this simulation, it's just equal to 1. So there is another question on the chat. Q-learn the policies maintain updated at every iteration of T, since at every iteration we update our estimate of Q and the policy is defined to be a function Q. What about SARSA? Is the policy updated only once after each complete cycle, or the critic? So these are all very good questions. To some extent, it's an algorithmic choice. I can tell you that Q-learning, as soon as you explore, you don't even need to link the policy that you use to take actions to the Q values. And so somehow the way you change your policy can be totally arbitrary, and I don't care as far as my convergence to Q star is concerned, as soon as you guarantee that you keep exploring the environment. And we have seen why it's so important, right, that you keep exploring the environment. For SARSA, you can get to the case where you really update the policy with the most recent Q value that you have at each step. So you do one step, you update the Q value. The new step, you will be using the softmax over those Q values to define the policy. And this is still sound and it's still convergent. So you can update somehow the actor very, very frequently, even at each step.